quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
It's my pleasure this afternoon to introduce one of our own alums from our physics department and returning as our visiting assistant professor in physics, Danielle Berg, to introduce Professor Krauss.
Okay, I'm really excited to be up here because I'm a little strange in that I really enjoy a little bit of awkwardness, and I have a feeling that this is going to induce a little bit of awkwardness and excitement in all of us, this talk and discussion to follow. Some of the questions that we are here to ask that we've been talking about is, why is there something rather than nothing? And if space is infinite, what is it expanding into? And is the ideas of multiverses a reality? And why does any of this matter? Our innate human curiosity has fueled our journey of scientific understanding and is why you're all here today. We seek to answer the larger questions of who we are, how we got here, and if we are unique, or rather, what is our place in this universe? The significance of these questions is profound, and it links us to the greater cosmos. As Dr. Filipenko talked about yesterday, in 1998, there were published observations of type 1 supernova that suggested the expansion of the universe is accelerating. Dr. Lawrence Krauss was one of the first physicists to suggest that space is composed of dark energy, making up approximately 70% of our universe by volume. Although we cannot see dark matter or dark energy directly, many of the scientists that are here today and others around the world are looking at its effects on the visible universe. Krauss has gone further by examining our current understanding of the universe in order to ascertain how we got here. By a universe full of stuff such as our own, how could it result from nothing by natural processes? So although we have many spirited young speakers with us today, and even younger Lawrence Krauss received his Bachelor in Physics and Mathematics from Carleton University in Ottawa and his PhD in Physics from the Massachusetts Institute of Technology. He is currently a Foundation Professor and Director of Origins Initiative at Arizona State University. He has published more than 200 scientific articles, many about the physics and astrophysics that we're discussing here. Krauss has also authored several celebrated books, which you can get in the bookmark across the way, hint, hint, including some really great books on the fear of physics, about Star Trek, about the atom, and a universe from nothing. Further, he's the recipient of numerous awards, including the American Association for the Advancement of Sciences Award for Public Understanding of Science and Technology, and the Julius Edgar Lilienfeld Prize of American Physical Society. He was even nominated for a Grammy Award for his liner notes for the Telarc CD of music from Star Trek. This guy has literally done everything. He has even received the Colbert Bump for his book, A Universe from Nothing. In his abundant spare time, he has been working on and created a documentary film called The Unbelievers with fellow renowned skeptic, atheist, and evolutionary biologist Richard Dawkins, which is currently being released in limited cities and I hope to eventually see. The film follows Krauss and Dawkins as they speak publicly around the globe about the importance of science and reason in the modern world. As a science educator and advocate, Krauss is also an active and respected member of the skeptics community. I bring this up because I first heard Lawrence speak at the amazing meeting in Las Vegas in 2011. After watching him stand up to a very spirited discussion with Neil deGrasse Tyson on the future of manned space missions, I was a little intimidated, but more so excited and challenged by the controversial ideas Krauss presented. As you may have noticed already during this conference, he is not afraid to voice his opinion, confront disagreement, or initiate thought-provoking discussion. From his exceptional taste in shoes, which you'll get to see in a moment, to being quoted via tweet by Miley Cyrus, or to his impressive IMDb webpage, I cannot think of a more interesting, passionate, or accomplished scientist to engage us all on the universe and its limits. To quote Lawrence Krauss himself, so don't get mad at me, the amazing thing is that every atom in your body came from a star that exploded, and that the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You can't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution, weren't created at the beginning of the time. They were created in the nuclear furnaces of stars, and the only way they could get into your body is if those stars were kind enough to explode. So forget Jesus, the stars died so that you could be here today. Whether that quote inspired you and left that awe-induced tingling feeling that I get in my body, or it rocked the boat for you a bit, I cannot wait to see what Lawrence shakes up today and the important discussions that will ensue. It is my great pleasure to introduce to you the sixth speaker of the 49th Annual Nobel Conference and his talk about a universe from nothing, as he challenges what you may think you know about the universe and its origins and ignite your imagination of what lies ahead. Please help me in welcoming a rock star of my scientific world, a man who is obsessed with nothing, Professor Lawrence Krauss.
Thank you. That worked. Thank you. Thank you, Danielle. Thank you, everyone here, Chuck and everyone else, for organizing this. It's been remarkable. First thing I'm going to do is get off the podium because I don't like podiums. I want to thank Chuck well, first of all, actually, as many of you can know, I like to try and one-up my colleague Frank Wilczek whenever I can, and I want to point out that this is better than his because I won't actually take off my shirt during the talk, so thanks to that. To Chuck, I want to thank him for allowing me to speak sixth after 2 talks on cosmology. So the talk with the universe from nothing, I kind of thought there'd be nothing left to talk about, and I figured that's what he would want me to do. But I'm going to try. I'm going to try anyway. And I think actually I've thought about there'll be some overlap, but Alex's talk and George's talk allowed me to build, I think, on some things that they've said and put them together in a way that I hope will enhance things. And really what I want to do, and this is really what I think all of the speakers has tried to do. It's one of my favorite quotes, and I began at least one of my books with it. I'm also, by the way, not going to use that stupid arrow because I've learned that actually, I checked empirically that you can actually see the screens from the back of the room. So if I do this and this, you can actually see what I'm doing. So it's easier for me to do that. But really, the most exciting part of any mystery is getting to the starting point. And hopefully what we've all done, and what we'll do today and yesterday, is get you to the starting point, because they're wonderful mysteries. And there are young people here who are going to carry on science the next generation. It's those mysteries that should inspire you. The science, we too often teach science as if it was, especially physics, as if it was done 200 years ago by dead white men. And it's not. They're full of mysteries. And I hope that you will be inspired to solve the problems that we've been talking about here today. In any case, okay, so let's begin. the question that Danielle mentioned is an interesting question. And why is there something rather than nothing? It's really inspired humanity since humanity's been thinking about that. How did we get a universe? How did everything we see get here? And it's been the source of constant speculation from religion to philosophy and science. And what's amazing is that science is beginning to at least be able to confront a version of that question. And that does upset some people, as we'll undoubtedly talk about. But what I want to show you is the amazing results that couldn't have been talked about at a Nobel Symposium 30 years ago. It's been a revolution in our understanding of the universe. It's allowed us the temerity to begin to address these questions, not answer them, but address them. And I think that's what makes it so exciting. Okay, so there are two ways to answer that question. One way is to write a book that begins like this. It doesn't tell you anything about anything. And now Frank may think I'm being provocative, but of course I'm really happy to see that my good friend George Coyne agrees with me about this. And I really always hesitate to say that George Coyne is a good friend of mine because I'm always worried he'll be excommunicated. But he is. But really, if we want to learn about the universe, the way is not to think about a book written before we even knew the Earth orbited the sun, but to ask the universe. And you've seen this image a lot in different forms, the Hubble Deep Field. But the way, if we want to learn about how the universe might have come into being, and ask those questions because it did come into being. And it's a physical universe, and if we want to address these questions physically, we have to look at the universe and ask the questions. And that's what I want to talk about. And the universe has changed our picture of everything more in the last 30 years than perhaps the last 2,000. And it's an incredibly exciting time. So, Alex talked a lot about Hubble and the expanding universe. I won't. There are two things I want to add to what he did. One is he didn't mention Hubble's most important characteristic, as far as I can tell, for the young people here especially. Because Hubble gives me hope for humanity. Because he began life as a lawyer and then became an astronomer. And so for all of you who are thinking of law school, there's hope for you after that. That's the first thing. The second thing is, especially with the questions after George's talk, and George happily once again showing us we're at the center of the universe, I thought I might also complement what Alex said a little bit to give you a different way of understanding that we're not. And this is useful, I think, because I often tell students that in physics, the first time you see something, you don't understand it. And the second time you say, oh, I've seen that before. And so and there's a lot of familiarity that helps with that regard. So anyway, this is Alex was kind enough to give me the version of the slide he showed before. This is what Hubble discovered, which is that everything's moving away from us, and we codify it in some relationship that the velocity of objects is proportional to their distance. And that makes it look like we're the center of the universe. And he gave one example, but I'd like to give a different one, which I think, for me at least, helps me understand that this doesn't tell us we're the center of the universe. It tells us that the universe is uniformly expanding. Now, the real problem is myopia. We are actually stuck in our universe. Well, most of us are. The Republican Party clearly isn't today. But you can... But anyway. So the way to see this is to get outside of our universe. And I can draw a universe we're outside of. Here's a universe that has galaxies at regular intervals. And just so you don't feel bad over here, I'll point these. And you can see if you're standing outside of that universe that it's a little bit later. It's expanded. The distance between all the galaxies is bigger. And the question is, what would you see if you lived in that universe? It's quite simple. Just pick a galaxy, any galaxy, say that one. And to see what you'd see, we just superimpose this image on top of this one, placing that galaxy on top of itself. What do you see? Exactly what Hubble saw. And the point is, it doesn't matter what galaxy you pick. There's the image that Hubble saw. Let's take another galaxy, put it on top of itself. Everywhere you are, everything is moving away from you. And that's exactly what Hubble saw. So what Hubble told us is there is no center of the universe, or every place is a center. It depends on how you like to think about things. But really what's important is that the universe is expanding. And the fact that the universe is expanding changed everything. Again, it's so permeated the public consciousness that the universe began, well, except in certain states like Arkansas and Ohio and a few others. That it began 13.8 billion years ago. But the fact that the universe began in a Big Bang is so much a part of popular culture that we forget that less than a human lifetime ago, that was not the conventional wisdom in science. The conventional wisdom in science, and when Einstein was developing general relativity, was that the universe was static and eternal. It had been around forever, and it would be around forever. It seemed reasonable when you looked out at the sky. And so the universe having a beginning changed everything in science, and also obviously in philosophy and religion. And it changed everything in science also because if the universe was dynamical, the natural next question was, if the universe had a beginning, how will it end? And Alex talked a little bit about that, and I'll talk more about it. Because if the universe is expanding, the natural question then becomes, will that expansion stop and recollapse in the Big Crunch or something else? And the answer to that question depends. It turns out remarkably, the only way to actually consistently describe an expanding universe is to use the laws of general relativity. Because general relativity is the first theory to describe not just how things move in the universe, in space and time, but how space and time themselves dynamically respond. And what Einstein told us is that space and time dynamically respond to the presence of matter and energy by curving and potentially expanding. And so what Einstein told us is that the future of the universe depends upon how space responds to the presence of matter and how much matter there is. And we present pictures of that, and I'll show a picture. It's always hard to do, because it turns out our universe, because space responds to matter, space can curve in the presence of matter. And that means it turns out, and Frank gave a beautiful talk on geometry, that our universe can exist in one of three different geometries, so-called open, closed, or flat. Now, it's hard to picture these. As Frank was pointing out, it's hard to picture a four-dimensional universe in general. It's hard to picture a curved three-dimensional universe because we live in a three-dimensional universe. So we draw pictures, two-dimensional pictures to guide the eye, but that's all they are. So here, it turns out in 2 dimensions, it's the same thing. You can have a closed universe, which is a surface of a sphere in 2 dimensions, a flat universe like a piece of paper that's flat, or an open universe like a saddle. But these just guide the eye. In a real closed universe, we're talking about the curvature of 3-dimensional space. And you can't picture that easily. You can write it down mathematically. We can talk about what it would seem like. For example, in such a universe, if you looked far enough in that direction, you'd see the back of your head. Okay? So we could talk about that, and it all sounds very nice, but what's really interesting, and the reason physicists cared about that, in fact, the reason I got into cosmology, because I got into cosmology because I wanted to be the first one to know how the universe would end. It seemed like a good idea at the time. And the answer depends upon, based on general relativity, on the amount of matter. Because if there's enough matter, and we live in a matter-dominated universe alone, then if you have enough matter to make a closed universe, while that looks nice and it's wonderful to talk about at cocktail parties, the important thing is, in a matter-dominated universe, the universe will expand to a maximum size and then collapse. In an open universe, it'll go on expanding forever. And a flat universe is the boundary between the two, where it slows down and never quite stops. And so the real question of 20th century cosmology became, which universe do we live in? Because then we know what the future will be. And if we want to know which universe we live in, we have to know how much stuff there is. Very simply, we just have to weigh the universe. It's a homework exercise. And that really, weighing the universe, became the business of 20th century cosmology, and I've written books about it. And you can talk about it for a long time, but like many things, a picture is worth 1,000 words. But I want to give you a perspective. We have weighed the universe, and I'll show you the results. To give you a perspective on this, I want to take you back a little time in history, I think, especially for the students. Some of you will become scientists, and you'll submit articles to journals like Science, and you'll be rejected. Okay? And I just want to tell you, you shouldn't worry. I want to take you back to a kindler, gentler time. It's a much more difficult time than it used to be. So I want to take you back to 1936. And there was an article that came out in Science magazine called Lens-like Action of a Star by the Deviation of Light in a Gravitational Field. And here's how it began. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Okay? Try that now and see what happens, okay? So, I mean, now the author had credentials. His name was Albert Einstein, so it kind of helped. But But what Einstein published there was the results of a calculation that he thought was completely unimportant. So unimportant he wouldn't have published it otherwise. He published results of a calculation. He'd earlier showed that light curved around a massive object. That's what made him famous, as was pointed out. But he realized if you had a massive enough object and you had a source of light behind that massive object, then the light could curve in both directions and come back and converge. And the object could act like a lens. It could magnify objects like my glasses do for nearby objects, or if I had a cut glass goblet, which you don't have here, I could look through that and I'd see many images of you. But he thought it would never be observable. He thought it was totally unimportant. In fact, it's kind of interesting. If you look at his calculation from his notebooks in 1936, you also realize that this is the calculation on which that's based, that actually he'd done exactly the same calculation in 1912 in his notebooks from 1912. He just forgot he'd done it. Okay? And my favorite part of this whole story is the note he wrote the editor afterwards. He said, "Let me also thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." Okay? That's how science is done, okay? And the great thing, of course, is he was totally wrong. It's not of little value. It's the way we weigh the universe. And here is the picture of the very phenomena that Einstein said would never be observable. And Alex showed a different one, but this is relevant. This is an amazing picture because it's a picture of gravitational lensing. It's a picture that results from the fact that space is curved. So you don't have to be a rocket scientist, as Sam Ting would say, to see that this is a cluster of galaxies. And as George pointed out, clusters of galaxies are the largest bound objects in the universe, maybe almost 10 million light years across from side to side. They're the biggest bound objects in the universe, and anything that can fall into anything will fall into a cluster. So if you can weigh the clusters, you can weigh the universe. And like many of the images you've seen before, every dot in this picture is a galaxy, not a star. Each of these galaxies contains hundreds of billions of stars. This is a cluster that's 5 billion light years away. 5 billion light years away. So the light from those stars left before the Earth even formed. Okay, and by similar token, if there were beings on that cluster that looked at us and saw the light that's happening now, we'd long be gone by the same time they watched. And in fact, most of the stars in this image may not even exist anymore. They may have ended their lives. And the civilizations that may have existed around them and had meetings like this are no longer. And I mean, I think that's really important because we may talk about spirituality, but this is real spirituality. When you look at this, images like this, they inspire you in ways that nothing else I know of can inspire. But in any case, as inspiring as that is, the really important thing is you don't have to be a rocket scientist to see that these blue things here are different. And what they are multiple images of a single galaxy located 5 billion light years behind that cluster. A galaxy that's so faint that without the magnification of that cluster, we probably wouldn't have even seen it. But not as only just one image, there are many images because the cluster, as a glass goblet would, splits up the light. It bends in many different directions. So this is proof, if you wish, that space is curved. But we don't need the proof because we know general relativity works. We tested many other ways. So now, as Frank talked about, we can now use it to test other things. And so we use general relativity. And the point is, now that we know general relativity works, we can use it to weigh this cluster. Because you can ask how much mass must there be in that cluster and where is it distributed in order to produce the image we get. Now that's a complicated thing called a mathematical inversion. It's relatively complicated to do, but you can do it, and Tony Tyson and others a long time ago at Bell Labs did it. And here is this cluster, and this is where the mass is as extracted from. In order to produce the image that was seen, the mass must lie in this direction here, in this way. And of course what you can see is spikes where the galaxies are. But really what's most important is you see a huge mountain of stuff where the galaxies aren't. There's 40 times as much mass in this picture as meets the eye. Most of the mass is where the stuff isn't shining. And in fact, around each galaxy there are little mountains as well. Most of the mass associated with each galaxy is not visible. And that's the stuff that physicists with their great linguistic perspicacity have called dark matter. And so we know that there's 40 times as much stuff in here, and it's dark, it doesn't shine, but what makes it particularly exciting, and one of the reasons we're talking about it is for reasons I won't have time to go into, maybe in the question period, I don't know. We have many good reasons to believe, not to believe, to understand that there's too much stuff there to be accounted for by all the protons and neutrons we know are in the universe. We know how many protons and neutrons are in the universe, and there's 10 times more of this stuff than is allowed by that. So that tells us that it's probably not protons and neutrons. That means it's some new type of elementary particle of the type we talked about, and Tara was talking about discovering at the Large Hadron Collider. And what makes that particularly exciting is that means we don't have to just look out there through telescopes for it. It's in this room. It's going right through your bodies as you nod off after lunch during this lecture. And that means we can build experiments to look for it. We don't have to use telescopes. And where do we build the experiments? Not here, because right now we're all being bombarded by cosmic rays. That would, if you put an experiment here, it would just have too much noise. You go deep underground, because most of the cosmic rays will be absorbed. But these dark matter particles, because we think they interact so weakly, most of them will go right through the Earth without even knowing it was there. And there are experiments being built around the world to look for that. Actually, takes me back. This is actually based on a proposal that Frank and I made 25 years ago or so, and then we didn't have to build it. So, but this is a dark matter detector that's actually located in Minnesota, deep underground. And it's kind of simple. You just take a little bit of germanium here and cool it down to about 1/1000th of a degree above absolute zero, which is what I'm told it is here in the winter. And then what happens is most of the dark matter particles will go right through the Earth without even knowing it's there. But every now and then, if we're right, one of them may bounce off a nucleus of germanium, and it'll heat the whole thing up roughly by 1/1000th of a degree. And so you put the whole thing underground and you try and shield it from radioactivity, and you hope maybe once a year, once a decade, once a century, you'll see a blip that can't be explained by anything else, and that might tell us the nature of the dark matter. And as I said after Tara's talk, the interesting thing is there's a race between the Large Hadron Collider and experiments like this to see if the dark matter is made of this stuff. One or both should see it, and that's incredibly exciting. But it turns out it doesn't matter what it is. Again, as I think Frank mentioned afterwards, it doesn't matter because we just want to know how much of it there is, because it's its gravity that will determine, we thought, the future of the universe. So let's go back to this and say, how much stuff is there when we weigh the universe like this? And we've come up with the answer. After 80 years, we've come up with the answer, and I'm going to show it to you. A drum roll. Okay, whatever. And there it is. Okay, there are people back in the room that are fainting right now. When physicists have an important number, we always give it a Greek letter to sound scholarly. And omega, which George alluded to, is a very important quantity. Omega, we call it's a quantity that defines for us the ratio between the actual amount of matter in the universe and the amount of matter to make an exactly flat universe. So if omega is less than 1, the universe is open. And if omega is greater than 1, the universe is closed. And you can see here, even from a long time ago, that at high accuracy, and the numbers have gotten better, there's only 30% of the amount of stuff to make a flat universe. So it looked like we got the Holy Grail. We'd finally figured out the universe is open, end of story, no need to have talks and such, etc. But there's a problem. The problem is we theorists knew the answer, because we always know the answer. We're not often right, but we always know the answer. Okay? And we knew that the universe was flat, because a flat universe is the only mathematically beautiful universe. And here these darn observers were doing what observers do so well, which is get it wrong, we thought. But there's clearly a loophole here, which is this determines how much stuff is around galaxies and clusters of galaxies. But what about all the stuff where there aren't, all the regions where there aren't galaxies? Clearly there's huge ways of missing stuff. And this is a very weird way of determining the geometry of the universe, because this really tells us the geometry of the universe, we thought. Because you have to plug the matter into Einstein's equations and then solve Einstein's equations, measure other quantities like the expansion rate of the universe, plug it all in, and from that try and infer the geometry of the universe. Wouldn't it be better to measure the geometry of the universe directly? And what's amazing is that we can, and we have been able to, and I'm thankful to George in some sense that he didn't talk too much about it, so I can. We have been able in the last decade or so to measure the geometry of the universe, which is just remarkable in the extreme. Now, how would you measure the geometry of the universe? Especially if you, let's ask how you could measure the Earth is curved if you couldn't go around it or you couldn't go into a satellite, okay? If you just lived in Kansas, how would you know the Earth is curved? Well, very simple. You draw a triangle, and you ask a Gustavus Adolphus student what are the sum of the angles in a triangle. You ask anyone else, and they won't know. But it's 180 degrees, but I'm assuming that they have a good education here, I can tell. And that's fine because we all learn our geometry from Euclid, as Frank pointed out. But in fact, on a curved surface, it's quite different. And in fact, he showed a slide about that. But on a curved surface like the surface of the Earth, I can draw a triangle as follows. I can go along the equator, then I can make a right angle and go up to the North Pole, and then another right angle and go back to the equator. And I got a triangle with 3 right angles. 3 times 90 is 270, and 270 is 180. So if I draw a triangle that was big enough on the surface of the Earth, I could prove the Earth is curved. And what is truly amazing is that same thinking works not just in 2 dimensions, but in 3 dimensions. If you could find a big enough triangle in our universe, you could measure the curvature of the universe. And that's what we've been able to do. People were trying for a long time. And we've been able to do it with the cosmic microwave background radiation that George so beautifully talked about. I remind you from George's talk that when we look out at the cosmic microwave background radiation, we're looking back at a time when the universe was a few 100,000 years old. Back to the moment when it became transparent. Now, seeing the images of that baby universe, and I'll show a different version of it, is amazing. It's worth a Nobel Prize or 2, in fact, at least 2. But what's equally interesting is there's a very important scale on that surface, and that's 1 degree. Because 1 degree represents, in general, in certain cases, and in a case that I'll talk about, 100,000 light years across on that surface, approximately. And if the universe is about 100,000 years old, Einstein told us that no information can travel faster than the speed of light. And if that's true, nothing on this surface over here could affect anything at that surface over there, because that's how far light can travel in the history of the universe. Okay? And certainly at that time that surface was created. Now that sets an important scale, because if I have a lump of matter that's smaller than that scale, what does that lump of matter do? As George pointed out, it collapses. And then it heats up and it does all the sorts of things that lumps of matter do. But if I had a lump of matter that's bigger than that scale, it doesn't even know it's a lump. It's like, I used to watch a lot of TVs. It's like Wile E. Coyote on the Roadrunner. If you remember, he used to run off a cliff and then he'd hang around a while before he realized he was supposed to fall. And that's exactly what would be the case. Lumps bigger than this don't know they're supposed to collapse. So the biggest lumps that can have collapsed or begun to collapse the moment the microwave background universe becomes neutral, when things can begin to collapse, as George pointed out, the largest lumps that can collapse are that big. But that creates a ruler for us. It creates a ruler that's 100,000 light years across. Well, let me just go back for a second. So that's a ruler, and it creates a triangle. We can ask, how big are the largest lumps? And to go back to this image, this is, again, I think something that Frank's slide showed, in a flat universe, and by the way, a flat 3-dimensional universe is not a pancake. It's just the universe you always thought you lived in, where the x, y, and z axes point in the same directions everywhere in space. Okay? In a flat universe, light travels in straight lines, and a 100,000 light year across ruler or lump should span on our eye 1 degree. But in an open universe, where light rays diverge as you go back in time, the angle spanned by 100,000 light year across ruler will be smaller. The ruler, the lump, will look maybe half a degree across. And in a closed universe where light rays converge as you go back in time, the ruler will look bigger. So all we have to do is take a picture of the types George took and ask, how big are those biggest lumps? And that's what we've been able to do. And the first experiment that began to really address this was not a satellite experiment. It was a ground-based experiment. It was in Antarctica. The boomerang experiment, it was called. Here's a balloon and a microwave radiometer, and it was sent up above the Earth to be able to look carefully at a small region of the sky. And that balloon went around the world, which is, of course, easy to do in Antarctica. If you're at the South Pole, you just do this. But it wasn't there. It was at McMurdo. So it took about 2 weeks to get around and come back to where it began. Well, it was called boomerang. And then it took this image, which superimposed on the original image. Here are the hot spots and cold spots of the type that George showed, as observed first by Kobe and then much higher detail by other satellites. But here they are, and the question is, these are the primordial lumps, as he pointed out, that were created at the very beginning of time, that would later collapse to form everything we see, the galaxies, the stars, the planets, etc. But the important question is, how big are they on average? So to see that, we can create universes in a laboratory. And on a computer, I guess I wanted to show the Planck picture just to show we do much better now, but I figured George would show it. And here's Boomerang. Here's that same region of the sky it looked at in a different false color image. And here are universes on the computer. We create a closed universe, an open universe, a flat universe, and we ask how big on average would those lumps look? And in a closed universe, the average 100,000 light year across lump would look that big, but that's bigger than these lumps. In an open universe, the average 100,000 light year across lump would look that big, but that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. And in fact, we now know to an accuracy of perhaps better than 1% that the observable universe is flat. So if you're a theorist, you can do this. Okay. Well, you shouldn't pat yourself on the back too much because, of course, there's a problem here, which I hope you're aware of. A few minutes ago, I proved the universe was open. We've only measured 30% of the amount of stuff to make a flat universe. And so there's a big problem. Well, if the stuff isn't where the galaxies are, it must be where galaxies aren't. But what is where galaxies aren't? Nothing. Now, the amazing thing is that we have learned, one of the great developments of 20th century physics, is that nothing is not so simple. When you put together the laws of quantum mechanics and relativity, then empty space becomes a dynamical thing, much more dynamical. When you put together quantum mechanics and special relativity, it turns out that there must be, that the empty space is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Particles we call virtual particles. Now that doesn't sound very impressive. It sounds like counting angels on the head of a pin. Okay? But so, the purpose of science isn't to invent things you can't see. That's the purpose of other things I won't go into at the moment. But so if you can't see them, then how do we know they're there? We can't see them directly, but we can see their effects indirectly. In fact, they're required and an essential part of understanding of modern physics. This image, which all of you have been staring at while I've been talking, I see, was actually something that Frank showed at the Nobel Prize ceremony. It's actually, while it's an animation, it's more than just that. It's based on real calculations. This is what the empty space inside of a proton looks like. Now, if you went to a good high school, and I'm sure the students here did, you learned that protons are made of 3 quarks, right? Okay. Well, we lied. Okay? They're not. They are made of 3 quarks, but it turns out if you add up the mass of those quarks, they account for almost a very small percentage of the total mass of the proton. Most of the mass of the proton comes from the fact of these virtual particles popping in and out of existence, these fields giving energy and mass to the proton. So maybe 90% of the mass of the proton or more is due to these virtual particles and fields. So you wouldn't be here if those virtual particles didn't exist. That's how important they are. So, and in fact, Frank won the Nobel Prize for the theory that allowed this calculation to be performed. So if we have a theoretical basis for calculating the contribution of virtual particles to the inside of the proton, why not apply the same ideas to empty space and ask how much energy would these kind of virtual particles give to empty space? And that's where you come up with the result that Alex mentioned. I notice kindly the 1 is missing from here, but if we do the same kind of calculation, we estimate that the energy of empty space is roughly a gazillion times the energy of everything we see. It indeed is the worst prediction in all of physics, although maybe some of my colleagues here have made worse, I don't know. But what we know is that the energy of empty space cannot be much more than the energy of matter, or we wouldn't be here. And so this problem has been around since before I was a graduate student, but certainly when I was a graduate student, and since then, which became called the cosmological constant problem. Why should the energy of empty space not be 120 orders of magnitude larger than everything we see? And as I alluded to in the panel earlier, we were able to go to sleep at night because we knew the answer, because we're theorists. And we knew the answer had to be exactly 0, because 0 is a beautiful number. More than that, there's a other more relevant physics reason. If the energy of empty space was not going to be bigger than the energy of everything we see, we'd have to cancel this big number to 120 decimal places, leaving a non-zero number in the 121st decimal place. No one knows how to do that. But 0 is a number we know how to get in physics. We have mathematical symmetries of the type Frank talked about and others they're mathematical symmetries that might cancel things exactly. So we all went to bed at night knowing that there was some symmetry of nature that would cancel things exactly, and the answer was 0, and so we didn't have to worry about it. But physics is an empirical science. And as I will argue in a bit, the universe doesn't give a damn what makes us happy. And so what we really want to know is that really the case? And the only way to do it is to observe it. Now, it turns out if you put energy in empty space, as has been alluded to in general relativity, it is remarkably gravitationally repulsive. All the people who've taken physics here know that gravity sucks, okay? But in fact, for empty space, gravity blows, okay? And that is remarkable. And that means if you look at the expansion of the universe, over time, if the universe is dominated by the energy of empty space, the expansion of the universe will speed up, not slow down. Now, as Alex talked about, in 1998, several groups of astronomers were trying to measure not that the universe was speeding up, but they were trying to measure the rate at which the universe was slowing down, because that's what a sensible universe should do. And to do that, they had to measure very carefully the expansion rate of the universe. And I just want to show, understand how much better the things are with type 1a supernovae of the type that Alex talked about. Here's Hubble's original data on the expanding universe from 1929, velocity versus distance. This is one of the reasons he was such a great scientist, because he knew to draw a straight line through that data set. And it's not so obvious. And he also did something else that astronomers have depended upon ever since then. He got the answer wrong by a factor of 10. They've tried to emulate that. He didn't do it because he was a bad astronomer. He did it for precisely the reasons that Alex talked about. To measure velocity and distance, you have to know the distance of objects, you have to have a standard candle. And it's very difficult to get standard candles, and the type 1a supernovae that he talked about have changed everything. Here's that picture he showed. I love this picture. It's of an exploding star as bright as a galaxy that's about 90 million light years away. And one of the other things I want to do just to add to what he said, to maybe emphasize this point, is that we can use these things. And here's a nice movie made by one of the two groups that he worked for. This is an exploding star. You can see its brightness over time and its colors, and it'll keep reproducing over time while I talk about it. The amazing thing is that you can do this, and he alluded to why, using statistics, but I want to just emphasize it from a slightly different perspective. If you went out tonight, and it's a clear night, and you held up a hole in your hand about the size of a dime, okay, where you couldn't see any stars, with the largest telescopes in the world of the type he showed, you could see 100,000 galaxies in a region that big. And if you do the calculation, once per 100 years per galaxy, if you can see 100,000 galaxies in a single image like that, you're bound to see a star explode, and people like him apply for telescope time to do just that, and they do it. And it's amazing. It's an important lesson. The universe is big and old, and rare things happen all the time. Another lesson that I think has implications in different contexts, as we'll talk about. Things sometimes just happen, even if they're very strange. Okay. This is to show you how much better you can do now. This is a modern Hubble plot with the type 1a supernovae. This was, of course, developed after the profound mathematical discovery that on a log-log plot, everything's a straight line. But still, aside from that guide to the eye, we can now use that to measure the Hubble constant to an accuracy of better than maybe 5%, not a factor of 10, as when Hubble got it wrong. And that allowed these groups, as he pointed out, to produce result, and this is actually, there was the cover of Science which is shown, but then afterwards, this is the two groups' data. This is the Hubble plot, this is the distance versus velocity, and the question is, what happens to it at very far distances? Does it turn up or turn down? And the way to see what happens is to draw a straight line through that data set and make the whole thing horizontal, so a straight line would be a horizontal line here, And what they and the both groups were looking for was to see how these distant supernovae would follow this curve going down, because that's what a sensible universe should do. And what they discovered, to their amazement, is that the supernovae didn't even lie below the straight line or on the straight line. They lay above the straight line. And there's two explanations of this. One, the data's wrong, which it usually is, but in this case it isn't. And two, empty space has energy, and the universe is accelerating. Now, if just for fun you try and fit the data and ask how much energy would you have to add to empty space, fitting the data, you get exactly what we were missing. If you put 70% of the energy of a flat universe in empty space, everything works. That's another reason why scientists are so quick to accept this result. Not just because it was a convincing result that the universe is expanding. There were lots of things that might have suggested that was wrong. But the universe is flat, only 30% of matter, and this fits exactly. So that is the cockamamie universe we live in. That is a profound result. We live in a universe, a flat universe, in which 70% of the universe is dark energy, this stuff the energy of empty space. Almost 30% of it is dark matter, and a little bit of cosmic pollution. Actually, 1% of it is what we can see. It's true that it was mentioned to be 4%, but most of that isn't even visible. If you look at the universe that we can see, if you take all the stars and galaxies and everything you can see on a beautiful night here in Minnesota and get rid of it and us and everything, the universe would be largely the same. So much for a universe made for us. We are a little bit of cosmic pollution in a universe of dark matter and dark energy. And it's changed everything, and I want to spend the rest of the talk talking about the implications. So let me summarize. The dominant energy in the universe resides in empty space. We don't have the slightest idea why it's there, and I want to remind you, we do not have the slightest idea why it's there. And in deference to my good friend Jim Gates, if anyone comes here and tells you they understand it, they're lying, especially if they're a string theorist. And its existence is tied, we think, to the very nature of space and time and to the origin of our universe, which is why it's so interesting to us. And as Alex alluded to, but I'll describe in a little more detail, it will determine the future of the universe. In fact, the reason I got into cosmology was the wrong reason, because it turns out geometry is irrelevant. It doesn't matter whether we live in an open, closed, or flat universe. The future of the universe is determined not by geometry, but by the energy of empty space. Okay. Now, I was going to ask for your apple. I meant to ask you, Alex, for it. But pretend I have Alex's apple here. You want a ball? No, it's okay. I'll just, this is good enough for me. It's more likely I'll catch it. So if I want to take you back to one of your favorite times in high school, which is high school physics, okay? We teach high school students how to calculate what will happen when I throw a ball up in the air. If I throw it up, as you pointed out, it'll come back down. If I throw it up faster, it'll come back down a little bit later. And if there's no ceiling, if I throw it really fast, it won't come down at all. And here's how we do the calculation. We turn it into bookkeeping. We say that the energy of an apple has two pieces. We call it the kinetic energy and the potential energy. It doesn't matter. There's a positive piece, which is the energy of motion. There's a negative piece, which is due to the gravitational pull of the Earth. And it just becomes bookkeeping. If the total energy, sum of the two energies is positive, the coin will escape. If it's negative, it'll come back to Earth. And that's what NASA uses every time they try and figure out how fast to throw a satellite up into space. Okay? But the remarkable thing is we can use that to discuss the universe as a whole. Because if it's expanding and it's the same everywhere, then what happens to every galaxy in the universe will happen to any galaxy. And therefore, if we take a region where we're at the center and ask what's going to happen to the universe, we just have to look at one galaxy that's moving away from us, and if it stops and comes back, then they all will. And then the calculation becomes just like an apple. We want to know the two pieces of the energy of this thing. The positive piece depends on its speed away from us, but that's what Mr. Hubble and others have told us. That's the positive piece. The negative piece comes from the gravitational pull of all the stuff inside, including the dark matter that we've discovered. So all you have to do is compare those two things, and you can determine, in a matter-dominated universe, the future. Okay? Now, the interesting thing is, if the negative piece beats the positive piece, if B over A is bigger than 1, then that region will collapse again. If b over a is less than 1, the universe will expand forever. But what is truly remarkable is we now know in a cosmic sense that b over a is nothing other than that quantity omega, which we've measured. We live in a flat universe. Omega is 1. And if omega is 1, then b over a is 1. And if b over a is 1, then b is equal to a. But if b is equal to a, the negative piece equals the positive piece, and that means the total gravitational energy of every object in the universe is 0. Now, if you were going to make a universe from nothing, what would you make the total energy? The first idea that maybe you can have a free lunch. And in fact, as Alan Guth has said, the universe is the ultimate free lunch. So now let's go to this question. Why is there something rather than nothing? The first answer to that, well, we have to be a little careful and describe what we mean by nothing. So the first kind of nothing is, say, the nothing of the Bible, of an infinite void, a dark, infinite, empty void, empty space. Well, that kind of nothing, it's easy to get something from. In fact, it's impossible not to, because that kind of nothing is unstable. This is what nothing looks like. We've seen it. It's virtual particles popping in and out of existence. Well, that's not real stuff. How can you get 100 billion galaxies? Well, when you add gravity to the mix, the reason these particles pop in and out of existence in such a short time is something called the Heisenberg uncertainty principle. When you take particles and you pop them into existence, they have energy. If they stayed there, they'd violate energy conservation because there wasn't anything there to begin with. So they have to disappear before you can see them. Quantum mechanics is kind of like the White House in corporate America. If you can't see it, anything goes. But when you have gravity into the mix, then these particles can have gravitational attraction, which produces a negative energy. And the total energy of the particle-antiparticle pair that pops into existence could be 0. And if that's the case, those particles can exist with impunity. There's no violations. And so you're guaranteed if you wait long enough in a universe that survives long enough, empty space will start spewing out particles. And you can get 100 billion galaxies worth of them if you had to. There's nothing that violates any of the known laws of physics to get something from nothing. You don't need supernatural shenanigans. Okay. Well, some people would say that that's not nothing. Because, after all, where did the space come from? You got the particles, but where did the universe come from? Well, the interesting thing is, and we don't have a theory of quantum gravity, I want to emphasize that. We do not have a theory of quantum gravity. Okay, we're working on it. Many people are, and many people think they have hints of it. But one of the things we know about any theory of quantum gravity is it's quantum mechanical. And quantum mechanics tells us that in space, particles can pop in and out of existence. Quantum fluctuations can happen. Gravity is a theory of space and time. If we quantize that, then space and time become quantum variables, and space and time could pop in and out of nothing. And I think Frank showed a picture which some people would, in different versions, could say is just that. Any theory of quantum gravity, when you put gravity and quantum mechanics together, it allows spaces and times to pop into existence. It means that there's no space, no time, and poof, a universe pops into existence. Now, most universes that pop into existence will pop out of existence, just like virtual particles, okay, in a microscopic time. What kind of universe could exist with impunity? A universe with 0 total energy. Now, it all begins to sound like it's all coming together, but it's not so simple, and I don't want to pretend it is. Because it turns out the only universe that we can actually mathematically prove has 0 total energy is not a flat universe, it's a closed universe. So what gives? Well, most closed universes, as you saw, will expand and collapse, and they'll expand and collapse if they created microscopically in a microscopically short time. The only closed universe that would survive long enough for us to ask the question is one in which there was a very early period of accelerated expansion that would puff it up so large that it wouldn't collapse right away. But that's precisely what particle theory now predicts. This theory we've heard mentioned several times, called inflation, predicts naturally, based on extrapolating the kind of physics we talked about, that very early on in the universe, there was a period of accelerated expansion when it increased inside by a volume of at least 10 to the 90th in a time frame of a millionth of a billionth of a billionth of a billionth of a second. It sounds like science fiction, but it's not. Now, what will that do? Well, what would inflation do? If it happened in the early universe, it would take a closed universe and puff it up. But if it puffs up, what would happen? Well, it's like puffing up a balloon and making it the size of the Earth. When you puff up a universe that's curved, you make it look flatter. And therefore, the only closed universe that could survive long enough to be enough for us to evolve, still can use that word here, is one that had an inflationary period, and therefore one that must look flat. So in fact, the only universe that can be created from nothing by this kind of mechanism and survive long enough for us to be around is a universe that looks flat, precisely like the universe we live in. And that's the point I want to mention. We can't show, because we don't have a theory yet, that the universe came from nothing by this. But it's plausible. And that plausibility is amazingly worth celebrating. But more than that, we can ask the question, what would a universe look like if it was created from nothing by just laws of physics without any supernatural shenanigans? And it would look exactly like the universe we live in. And that is remarkable. But that's not enough. Because some people would say that's not nothing. Because you don't have particles, you don't have radiation, you don't have space, you don't have time. But what about the laws? What about the laws themselves? Well, it turns out that even the laws of physics themselves may be accidental. And to do that, I want to answer the question Sam asked, actually, in the panel a little more rigorously. And Alex alluded to. It's this amazing coincidence. This is a brief history of time. That's the last, as George would say, it's the last complicated picture I'm going to show you, so it's downhill. This is the density of matter in the universe as the universe expands. The density goes down. This is the density of empty space, energy density of empty space. It remains constant. And we live in a time, 13.8 billion years after the Big Bang, when the energy of empty space is roughly 3 times the energy of matter. That's the present time. But when you look at this, or when physicists look at this, they go crazy if you stare at it long enough. Because Copernicus told us it's not supposed to be this way. Why should we live? We live in the only time period in the history of the universe when these two numbers are about the same. When the energy of empty space is almost the same as the energy of matter. Why should that be the case? It's not supposed to be the case. There's nothing special about 13.8 billion years. There's nothing special in the fundamental constants. We should just live in an average time. Why are we living in such a special time? Well, physicists have thought a lot about this, and one of the answers is here. Galaxies exist, as was pointed out, and I want to explain that. Let's say the energy of empty space were 50 times greater. So that line, instead of being here, was up here. Well, then these two curves would cross at a different point. They'd cross, in this case, at the point when galaxies first formed. But if the energy of empty space was greater than the energy density of matter before galaxies formed, galaxies wouldn't form, because the repulsive force would beat out the attractive force. So if the energy of empty space were much bigger than it is today, galaxies wouldn't form. And that's led some physicists to something I like to call, well, anthropic mania. The argument is perhaps there are many different universes, and the energy of empty space is just a random variable. It changes in each universe. Then only in a universe in which it's not much greater than we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because there are astronomers here to measure it. It sounds funny. It sounds almost religious. It sounds like purpose. But it's not. That's a mistake. It's the same mistake you make if you assume the fact that bees can see the colors of flowers is because they're designed to do so. That's due to evolution and natural selection. This is a kind of cosmic natural selection. We would be amazed to find ourselves living in a universe in which we couldn't live. That would be worth writing a book about. So it may just be a remarkable accident associated with our existence. That the reason we find this value is that if it were different, then we wouldn't be around in our universe. It's awful, of course, because it turns physics into environmental science, God forbid, but nevertheless, it may be true. But particle physicists have jumped on this because particle physics is way ahead of cosmology. There are many more problems we haven't understood for much longer than cosmology. We don't understand why gravity is the weakest force in nature. We don't understand why the proton is 2,000 times heavier than the electron. We don't understand why there are 3 generations of elementary particles. Those are the kind of things that Tara and her colleagues are trying to address with experiments, and theorists are also trying to address. So some physicists have jumped on this and said, this is great. We don't have to understand anything. Maybe it's all an accident. Maybe it's just, if it were different, we wouldn't be here, and then we don't need a theory of everything. We just need a theory of anything. But we have such a theory. It's called string theory. So I want to give, before George, Jim may give a longer version, but I'm going to give a short version of string theory. So this one guy says to another, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. The second guy goes, okay, what would that imply? The first guy says, I don't know. So that's a history of string theory over the last 40 years or so. And it's had its good times and bad times. But one of the things that nevertheless, and it's a well-motivated theory, I don't want to make any more fun of it, but one of the problems and opportunities, I suppose, of string theory is that it, in general, requires many more dimensions than the ones we actually see and measure, 10 or 11 in most of them. And the question is always, where are those dimensions? We don't see them, and one way to get rid of them is to curl them up into very small volumes. But what's amazing is every different way you curl up those extra dimensions in string theory, you end up with a residual universe with different laws of physics. And so some people realize there may be 10 to the 500 different possibilities. Even if there's only one string theory, there may be 10 to the 500 different four-dimensional universes that could result, each of which would have different laws of physics, depending upon how you compactify these extra dimensions. But then, you see, then you're guaranteed to find a universe like ours. Because in each universe, there could be different laws of physics and the different energy of empty space. One of them is bound to look like ours. Now, is that science? I mean, if you have something that's consistent with any possibility that could ever arise, it's an interesting philosophical question, whether you have a scientific theory, and that's something to be discussed. But whether it's not, is or not, it may be true. Whether I like it or not, and I don't. What I've learned is that, again, the universe doesn't give a damn what I like. And so this may be true, but if this is true, when a universe pops into existence, the laws of physics pop into existence along with it. And so you got no space, no time, no particles, no radiation, no laws. To me, that's a pretty good approximation of nothing. Now, I want to end with another version of nothing. It was one that came to me from my late, very good friend, Christopher Hitchens, because I used to talk to him about science a lot. And when I told him about this, he said, you know what? Nothing is heading towards us as fast as can be. And I want to allude to the future. Alex talked about it a little bit, but the first person to realize the future was really miserable was of course, George Orwell, who said, to see what is in front of our eyes, one's nose requires a constant struggle. Okay? And this is clearly what he meant by it. What he meant is that if you put energy in empty space, constant energy, the universe is going to expand, and it's going to expand faster and faster and faster, and something that really hasn't been alluded to is eventually objects will be moving away faster than the speed of light. That's allowed in general relativity. We teach you that nothing can move faster than light, but we lie. Well, you have to be like a lawyer and parse it a little more carefully. Nothing can travel through space faster than light, but space can do whatever the hell it wants. And if empty space has energy, there are regions now which are, well, in fact, there are regions now moving away from us faster than light, and we can calculate that. In fact, we can calculate the distance away from us beyond which objects are now moving away faster than light. It's 18 billion light years, and the universe is 14 billion years old or so. So these effects are just beginning to be visible, and they're going to get worse. Because when objects are moving faster than light, we can't see them. The light can't make it back to us. They literally disappear in ways that I don't have time to discuss. But I've tried to use this, indeed, Alex, before Congress to say that we should measure things now while we have a chance. But the time frame of this happening is like, of what I'm going to talk about happening is 2 trillion years, and that's a lot longer than the long-term future for a congressperson, which is 2 years. So it doesn't work. Yeah, it never gets to us. Okay, but this means, and it's been alluded to, but in a much more dramatic way than I think it's been alluded to, the rest of the universe really disappears. And this means, in the far future, as was pointed out, I find it quite poetic. I said that a single human lifetime ago, we thought the universe was static and eternal. What I didn't say was that Hubble also was one of the people who discovered there was more than one galaxy. In 1925, the picture of the universe was that it was static, eternal, and the entire universe consisted of a single galaxy, our Milky Way galaxy. In 88 years, a single human lifetime, we've discovered 100 billion of them. That's why we're like the early map makers, just beginning to understand the universe on larger scales. It's not surprising that we're surprised all the time. But in the far future, it's very poetic. There'll still be stars around in 2 trillion years. There'll still be main sequence stars. And astronomers on those main sequence stars will evolve because there'll be carbon, and they'll evolve, and they'll discover the laws of physics, of quantum mechanics, of relativity. They'll build telescopes, and they'll look out, and what will they see? Nothing outside their galaxy. The universe that they believe they'll live in will be the universe we thought we lived in 100 years ago, with a single galaxy, and all evidence of the Big Bang will have disappeared. But after that happens, these stars will burn out, and the universe will become cold and dark and empty, as Alex said. So in that case, as Christopher put it, the simple answer to the question, why is there something rather than nothing, is just wait, there won't be for long. And I think that's the most important answer because it demonstrates our incredible cosmic arrogance. Many people think we're the pinnacle of evolution, but it's not as if evolution had some purpose to get to us and it stopped. Okay? And many people think the universe that we live in is the universe is the way it always was and always will be. It's not. It's going to be quite different. And we won't be around, and there'll be nothing around in the far future. So, to conclude, science has demonstrated that a universe from nothing is not only plausible, I would argue, but likely. And what's really important is that what we mean by something and nothing has completely changed from the time the classical philosophers and theologians first raised the issue thousands of years ago. That upsets some people when I say that science has changed the meaning of things that came out of it. But it's actually called learning. Okay? We should celebrate it. And really, the important thing is that I want to point out is why is there something rather than nothing is not the important question. In fact, it's not even a reasonable question. Because why is there something rather than nothing assumes purpose. Whenever you ask a why question, it assumes purpose. In fact, why questions are fundamentally meaningless. Whenever we ask why, we really mean how. And anyone here who's a parent knows this. When your kids ask why, the only answer inevitably is because go to bed. Okay? What really is the important question is how. How did the universe evolve, and how can we find out? And that's what we're celebrating here today. And the amazing discoveries we've heard talked about are continuing, and the surprises that are going to happen, what we now know will pale in comparison to what the young people here will discover, as some of them, I hope, become scientists. So, to really conclude, I've told you 2 things. First, you are much more insignificant than you ever imagined. And second, the future is miserable. Okay? But you should be happy. Because, you know, we may live in a universe without purpose, but what does that do? That means the purpose in our lives are the purpose we create. And we should consider ourselves fortunate to have evolved in this place in the middle of nowhere and evolved a consciousness where we can understand the universe from the earliest moments of the Big Bang to the far future, sitting here in this remote place in the middle of nowhere. And so instead of being depressed, you should enjoy your brief moment in the sun. Thank you very much.
Thank you. Thank you, Professor Krauss. That was the best talk I've heard about nothing ever. At this time, I'd like to bring the panelists up for the question and answer period. And in a couple minutes, we'll get started with the Q&A session. Please pass your questions to the ushers as they come around. Great job.
That worked. I was able to build on what they said, so I felt good about it.
Yeah, it's really good. That's good.
Thanks.
Yep. You got everything you need?
Yeah, I'm just going to put all this stuff away while I'm Yeah, no, in fact, I mentioned your name. I didn't make you happy? How can I not make you happy? Okay, I know, but it wasn't about you, yeah. I don't worry about it. Yeah, no, I know. I know it's safe to say it's you.
Hello, excuse me.
Yeah?
I really enjoyed your talk.
I think we got to do a panel, but I'll sign it.
Could you sign it?
Will you be here after? Okay, I'll quickly sign it.
Okay, thanks. Thank you.
Thank you. We're going to do the talk and then I'll sign it.
Okay,
Thank you. Okay,
thank you.
take care. I thought I'd thank you. Your audiovisual was perfect. If you want
I'll go ahead and get your power supply while then.
I think one of them. He's coming. Okay. He's already on. That way we can get started. Okay. I'll get the crowd set. Yeah. I mean, you can have them start this. It doesn't take you guys long to get one person ready. Okay, folks, we're going to get started in just about a minute here, so if you could find a seat, pass your questions to the ushers, and we'll bring them up front for us. Thanks.
Okay, we'll begin the Q&A session now with questions from the panel, and we'll start with Professor Filipenko.
So, thank you, Lawrence, for that very interesting talk. I wanted to clarify one issue, though. There are many issues, but one can imagine a universe spontaneously forming out of nothing as a result of quantum fluctuations, essentially, and then inflation making it grow, and it has essentially zero energy. But does it presuppose an existing set of laws of physics?
Well, it's a good question. We were talking about it before this began, but what I wanted to point out, obviously, the answer is yes and no. because
the answer is yes.
It could be that all possible laws occur. It could be that all possible combinations of laws, multiverse doesn't have to be finite. It could be that every possibility that can happen happens, and therefore every possible set of laws of physics may exist. And that's the same, it seems to me, as having no laws. And basically, it's saying that there's no selection effect. It's just anything that can happen happens. But it could be, and in fact, in the case of string theory, there is some underlying law. And in fact, you didn't say it explicitly, but I'll say it. I assume quantum mechanics there. In order to have quantum fluctuations, one has to assume quantum mechanics. I don't know how to, I can only work with what I have as a physicist. There could, as far as I know, it's possible that quantum mechanics itself may not be universal. We don't have a fundamental law of physics. So the answer is, of course, one doesn't know. And not knowing is a wonderful thing. And so there may be a unique set of underlying laws in an 11-dimensional universe. There may be every possible set of laws in the universe in this multiverse that can happen. And my point is, therefore, that it's not as if you need. If we ask what people really mean when they ask, what's the miracle of existence? Most of the time they say, how can you get the stuff we have unless someone said, let there be whatever? And the point is, it's not a miracle to have stuff where there was no stuff. That's no miracle. It's not a miracle to have a universe where there was no universe. That's not a miracle. And you don't have to have a uniquely set of prescribed laws of physics for our universe to arise. Indeed, there may be some underlying law of physics in the universe, and I don't know the answer. But that doesn't, to me, the important question is, how did our universe get here? And maybe I push this question, why is there something rather than nothing, back to the multiverse. I don't give a damn. It's not the thing that interests me. The interesting thing that interests me is, how did our universe get here? But it's an important question.
But even the multiverse, its existence is difficult to comprehend unless there's some underlying set of laws that allows it to.
But difficult to comprehend is different than existence. That's what's wonderful about physics, is that things that were difficult to comprehend happen. And we've been able to comprehend them. There may be ultimately things we'll never comprehend. I'm one of the people, I don't think we'll ever have a theory of everything. I would be amazed if we did. And I think that's the wonder and beauty of science. The mystery is what makes life worth living. And so, absolutely, I can't comprehend the words you're using. I can't comprehend mathematically, because I don't. If I could, I'd write it down in a physics paper. And so you're absolutely right. These are issues we don't understand, but they don't take away from the remarkable fact that it used to be that life was a miracle and had to demonstrate something beyond the laws of nature. Happily, Darwin got rid of that. And I would argue that physics is getting closer to the point of saying, at least to understand how our universe got into existence, we don't have to posit anything supernatural.
I'm ready.
Wow. Frank?
Lawrence.
Go ahead.
Okay, Lawrence, first of all, stellar performance. I'm sure the audience appreciated it. And for these...
Okay, thank you.
And since you're such a great supporter of the string theory community, I want to thank you for your comments.
I like to give you free advertising wherever I can.
Thank you very much. But my serious question is the following. You might be surprised, at least in my own personal views of physics, that I find a lot of resonance with what you say. And in particular, the whole question about whether the laws of physics themselves actually had some sort of natural selection to act upon them. Would you be surprised if I told you that I, in fact, accept that and have some minor evidence that that is true?
Well, I wouldn't be surprised. First of all, I don't think you should accept anything. That's really a key point. So you shouldn't believe anything.
Well, when I say accept, I mean provide my own internal proof.
Okay. I mean, if you could see evidence, then that's a good bit. there's lots of indirect evidence, and I happen to think the phenomenon of inflation is the best motivated evidence that there might be a multiverse. It's my opinion. But no, I wouldn't be surprised that if you agreed, because I've known you for a long time, and you're a sensible guy.
That sounds like a cop-out to me.
So when you're saying evidence, do you mean a prediction that we can test experimentally?
No, I do not.
You want to give it? I mean, everyone's wondering. So why don't you give it?
Well, actually, some of the people in this auditorium have actually heard a talk. There, you know, Lawrence, I've been mucking around down in the mathematics of supersymmetry, and we have found these weird, and some people say unimportant, but evidence of what looks like error correcting codes. There's only one place in nature, in the observed world that I know, where error correcting codes occur, and that's in natural selection. And it's even not completely clear there, but there are, as you know, geneticists who make that argument.
I mean, it's fascinating. I'm skeptical, but it's you know, it's great. I think and it'll be amazing. I think what's amazing, and what I try to illustrate, is that we can even ask these questions. We could have had a symposium 30 years ago, a Nobel symposium, and we could have asked the questions, but we wouldn't have had any sensible. I mean, I'm not sure you'll argue that my answer is sensible, but we know so much more that we've gotten to the point where these questions are even discussed among scientists, which I find fascinating.
I think a lot of the issue that Alex was raising and many people raise in this connection is, what exactly do you mean by nothing?
Well, I thought I made it clear.
No, it was obviously not entirely clear. As you know, almost exactly 30 years ago, in fact, I made a proposal very much along the lines that you discussed here in Scientific American, with a rather precise, however, formulation of what nothing means. What I took as nothing is the idea that the universe would begin in a very, very symmetrical state with no matter and much more symmetry. The symmetries that are broken in our world would be restored. We know many of them are restored, so we could assume that there was a much more symmetrical state early on with, for instance, equal amounts of matter and antimatter. And then I think it was already plausible then, and it's become, as you mentioned, much more plausible now, that the laws we know operating on such a state could lead to something very much like our universe. But I wouldn't overstate how that means you're getting a universe from nothing. You're getting a universe from a framework of an assumption about what the initial state is and what the laws are. And both of those are certainly still up for grabs to a large extent, especially the assumption about what the initial state is, or even whether we should assume an initial state. For instance, one can sensibly speculate about whether that's the right formulation at all. Maybe the right formulation that would be more symmetrical would be to say something about the final state.
Yeah, no,
I mean, cosmology, as you know, is a subject that's changed a lot. You emphasize that, in fact. And I don't think it's over yet.
Well,
even at a very fundamental level.
Well, I think obviously I resonate with a lot of what you said, and I agree that one should be careful, as you should have been careful when you wrote the Scientific American article and and said, why is there something rather than nothing? Because nothing is unstable.
That's right. That's exactly what I said. Yeah.
And so we all use these terms, and what we mean, I think, look, one can have a huge philosophical discussion about the nature of nothing. I think it's largely a waste of time myself. But what we operationally mean is that you might say nothing is non-existence. And the question is, how could you get something that exists now from something that didn't exist before? That's the weird thing. Now, whether there was absolutely nothing else is an interesting question, but it's not the question I think that one's addressing. How can you get something that exists when it didn't exist? And actually, that's no surprise. People seem to find it a surprise. You know, look at the light from the photons are coming from that light. Well, they were emitted spontaneously by electrons that jumped between levels in atoms. Did the photons exist before the electrons emitted them? Absolutely not. So they're photons that came into existence. It doesn't bother anybody. Somehow it bothers people when we talk about a universe. So you're absolutely right. One has to be careful.
No.
But I tried. No space is one version of nothing, but no particles, as you pointed out, is one version of nothing, but no space is a much more interesting version of nothing. No space and no time. And pointing out that even a space can come into existence when it wasn't is a fascinating thing to talk about. And maybe
But I think you're overstating how much that can be done. You need something, you need a space out of which another, you can have more space arising out of some space.
No, I think
But
I think no, hold on a second.
It's very
We agree that that a space-time which didn't exist, a four-dimensional closed universe, could come into existence that wasn't into existence before. You will agree
But
with
it
that
doesn't
statement.
start from nothing. It starts from a special initial.
But it doesn't start from a universe that existed before, because that universe wasn't there.
Well,
that's my
what you
point.
mean by a universe.
Well, the rest is
Depends what you mean
semantics.
by nothing. No, it doesn't. It's well.
No, I mean, I think it's a remarkable thing that a universe can have zero. Well, you're not the only one who can interrupt, Frank, but it's a remarkable thing that a universe can have zero total energy and come into existence
No question. No question.
That's all I wanted to point out.
That when Einstein first learned about that, he almost got himself run over by stopping in the middle of the street in Princeton.
Yeah. No, and so I think ultimately
It's
we're
a
in
striking
agreement.
observation. There's no question.
Yeah.
But I think the thing that confuses and upsets some people, and well, in fact, I know it does, and
at least
not
one
me.
person.
It doesn't bother me. I don't care.
Oh, okay.
Except because of my sympathy for other people.
For humans.
But when you say nothing,
you said
it. That's you're threading your title. It means something to. It means different things to different people.
That's why I tried to find
when I
it.
said
I had
nothing,
three
I
versions.
tried to be careful about what I meant by nothing.
So did I.
Well,
I defined three different versions of it. Anyway,
I think once you start talking about the laws being random or no laws at all, you could really start from nothing at all. I think that's going too far. I think that it's really within a specific framework that you can discuss these questions.
Well,
and you definitely invoked quantum mechanics, you invoked relativity, you invoked a lot.
Absolutely. I gave an example by which the universe could come into existence, but I made a key point that we don't know.
Lawrence, what do you mean by exist?
Well, that's a good question. It means having a panel discussion. Well, as a physicist, what existence means to me is that I can measure it. Or not that I can measure, that Tara can measure it.
And
or
that's fine.
Sam, someone else.
That's fine, but that does not exhaust the meaning of exist.
You're right, but it's all that I care about.
Okay.
Okay?
It's fine.
Okay, I mean, seriously, it's maybe my own limitation. Yeah. But if I can measure it, then as a scientist, if I can't measure it even in principle, obviously we've all created, the theorists on the panel, things we can't measure. But in principle, we can imagine them being measured. And as a scientist, if it's not related to that, it's just not science.
Right. So I would like to sort of tie that with what Frank was just saying. And that is, 30 years ago, you couldn't have this discussion. And 30 more years, you're going to have a really different discussion. I mean, the fact is, we're putting in a lot of scientific cultural prejudice into our models, and it is true you can make up a model in which you get the universe we're living in today from a place that had no space and time and no particles and energy or something. That's perfectly a reasonable prescription you can kind of do. I've actually assigned it as a homework problem and have my students choose the coefficient of the area functions to get the universe of their design. But it's much more difficult to be arguing about how to remove the context and how to do that. Yes. And so this is where I have to voice my.
What do you mean how to remove the context?
Well, so one of the contexts that both of you talked about are the multiverses and the anthropic principle, and those are arguments about what's going on. But I can give you examples of universes that are much more probable than the one we live in, and examples of universes infinitely more probable than we live in. Yeah. And therefore,
it'd be great
even though rare things happen, we shouldn't have happened, right?
No, actually, that's the important thing. If it were really physics, It would be great, and one of my problems with I've worried about multiverses is that if we had a theory that allowed us to calculate the probability distribution over universes, well, that would require having a theory of the multiverse, which we don't have. Anyone who talks about probability distribution doesn't know what they're talking about because we don't have a theory yet. We can guess the probability.
Right, but if you're going to do the anthropic principle, you're immediately putting in probability distributions.
Well, you're assuming a selection effect, but you're assuming the probability distribution, but you don't. That's the problem with the anthropic principle, is it's always based on ignorance. Because if you really had a theory, you wouldn't have to use the anthropic principle anymore. You just calculate.
Right.
Lawrence, can I ask a really dumb question?
Yeah, I'm biting my tongue, but go ahead. Yes.
You agree that space and time come into existence, yes?
Probably. I wouldn't
It's happening
say
right now in this room.
No. I mean,
it's a serious question.
As you're well aware, there are models of bouncing universes that I find particularly ugly that go through something at which you have to do Planck scale physics. But you could have imagined an eternal universe that bounces. It doesn't obviate anything that I talked about.
But my point is, you talked about the dark matter particle going through the universe. In this space, it's expanding, right? And time is growing, right?
What? Where? The space between you and me isn't expanding.
Between my hands,
gravitation.
between us and the audience, right? It's just that gravitationally we got corrections going on.
Yeah, well,
but
it's
the
not
fact
expanding.
is, space is being created all the time, right?
Yeah, so?
So that was the question, right?
But if I could get back to my question, the point's much simpler. How do you have dynamics without time?
That's a wonderful question. I wish I had the answer. But the point is that when people talk about, in fact, one of the arguments, look, I've just come from Australia where I was having this debate with a Christian apologist. And the argument given of cause and effect, that there had to be some purpose because there has to be, the cause and there has to be universal, the first mover, all the rest of the stuff. The point is, you're absolutely right. If time comes into existence at the same time as space, then the question of what happened before is not a good question.
It's not a scientific question.
It's not a scientific question. But I'm not sure it's not a scientific question. It's not a question we can answer yet because we don't have an understanding of that theory and how time can exist. I don't think you will agree with me that there's a vast difference between things we don't understand and things that are not understandable.
Oh, absolutely.
And so it's absolutely true that I can't, as a physicist now, adequately discuss what I mean by universes without time. But that doesn't mean that someday one of the young people sitting here won't.
No, but I'm just saying that's an obvious hole in the argument.
There's a what? That's a what?
That is, to me, the most obvious hole in the argument. I don't know how to talk about dynamics without time.
Well, you can imagine, you can. You can imagine, you can imagine a super space, and I wasn't going to say superstring, argument where you have a Hamiltonian and things look like they're static, but locally they're dynamics when you take part of the system. You know how to do all that.
Yeah, but then you have a pre-existing space in which there are laws of physics.
Not space.
And you haven't.
You don't our
yeah,
space.
but you have a pre-existing entity of some sort.
I don't care if there's a pre-existing entity. Our universe did not exist. It came into existence. That's the thing I wanted to discuss. And I don't see why people are worried about stuff we can't discuss. We can discuss possibly how our universe came into existence. Isn't that good enough to be celebrating on a nice afternoon in Minnesota?
I like it, but I want to know what happened beforehand.
Well, I would too, but I don't know.
I think we're all happy to celebrate the idea that we've progressed enormously in recent decades, and our understanding has pushed back the frontiers of what needs to be assumed as unexplained within our description of the universe. But I think it's far from the case that we pushed it all the way back to nothing.
Well, I think we're in agreement. Because the point, and if you listen to carefully what I said and what I write, right. I never say we've pushed our understanding back to nothing. We've made certain postulates plausible, and that is fascinating. Darwin did not understand DNA when he, or the mechanisms of genetic mutation when he developed natural selection. What he showed, it was eminently plausible based on the fossil record and what he knew, that all the diversity of life came from a single life form. We now know much more. And what's great, I mean, and what I really want to do, and I want to emphasize, is not overstate what we know, but the very fact that we can begin to address these questions should get people interested in thinking about them as scientists.
Maybe, I mean, a position that I'm very comfortable with, and have been for a long time, is that the ultimate laws that govern the universe, including both the laws and the initial conditions, or whatever substitutes for initial conditions in a final formulation, will turn out to be simple and beautiful. But it won't be 0 equals 0. It'll be something richer than that.
Well, that's nice, but that's much more speculative than anything I said. It's a nice idea, but
no, it's not.
we don't know it'll be simple and beautiful. I mean, it's a nice. I'm glad it makes you happy. But,
I think it's what you're groping for.
But but what's actually what's equally plausible, and I thought you were going to say, is that there may be no such thing as initial conditions. Initial conditions may be inseparable from final conditions, and their very question itself may be a bad question, and that's great. That's great, and science will, and that may change the picture. Yeah.
Well, but we don't know yet.
We don't know yet. And let's celebrate.
And we're pushing things. We're pushing.
Well, I'm pushing you.
But we're not. What's that? We're not pushing you. Okay, we'll try to pull you in.
I want to take a question from the audience and contextualize it a little bit. We've heard some talk about string theory not being physics because it's not testable.
I didn't say that.
Well, no, you would never say that. No, Jim's your friend. Is the multiverse theory physics? What this person is asking is, can we design or conceive of an experiment or set of experiments to explore the concept of the multiverse?
That's a really good question. Are we just talking metaphysics, or is it physics? Is the multiverse physics? Because in principle, although it's possible in certain multiverse theories that universes can collide and then you'd know about it before you ended existence. But it could be that, and it's quite likely that if we're part of a multiverse, that we'll never have direct causal information about the rest. But I think it can be science in the following sense, that atoms were science before we knew about them. Namely, before we could measure them directly. One could imagine that we did have a very good theory that explained why there are 3 generations of elementary particles, why the proton is 2,000 times heavier than the electron, et cetera, et cetera, et cetera, why gravity is much weaker than the other force. And it could be a corollary of that theory that, in fact, we can actually predict that inflation must have happened, for example. And then we can make 50 predictions we should compare with experiments. But one of the inevitable logical consequences of that theory is that there's a multiverse. So we can probe 49 aspects of that theory and test them, and then we're willing to say the one equally logical consequence that can't be removed also must exist. So I think that's science.
I agree very strongly with that. In fact, I think we have an extremely useful and profound example of a theory that's very rich in consequences that can't be verified, and that's quantum mechanics. Quantum mechanics works on wave functions that have much more information in them than we can extract even in principle. So.
Yeah. Okay, we're in agreement.
Let me put forward one final question from the audience, because I thought of it too during your talk. This idea that during the inflationary period we had sort of a closed universe, but it inflated so fast that what we measure appears to be flat. And the questioner wants to know, is our determination of the flatness due to our measurements, which you showed, it's really closed, but our measurements make us think it's flat because it inflated so fast?
It's obviously a good question. What we need to say, and we often need to be more precise, and me too, and we tend to say things. What we mean is that the measurable, observable universe is indistinguishable from a flat universe. But the definition of universe has changed, of course. The universe, what we mean by universe is now that which we are in causal contact with, or ever could be in causal contact with, or ever will be in causal contact with in the future. And that's not everything. And so if that picture I gave, which is one version, which is that a closed universe is created, if that's true, then on sufficiently large scales, that closed space-time is curved. But inflation generically, although not universally, but generically produces so much expansion that it's that the difference between omega equal 1 is in the 50th decimal place or something. So if we waited, in a universe that lasts forever, if you waited long enough, you might see some evidence for that, except in a universe that happens to be dominated by vacuum energy, all that information will never be recovered because the rest of the universe will disappear.
Okay, we will close now and reconvene at 3 o'clock for Father Coyne's talk.
quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
It's my pleasure this afternoon to introduce one of our own alums from our physics department and returning as our visiting assistant professor in physics, Daniel Berg, to introduce Professor Krauss.
Okay, I'm really excited to be up here because I'm a little strange in that I really enjoy a little bit of awkwardness, and I have a feeling that this is going to induce a little bit of awkwardness and excitement in all of us, this talk and discussion to follow. Some of the questions that we are here to ask that we've been talking about is, why is there something rather than nothing? And if space is infinite, what is it expanding into? And is the ideas of multiverses a reality? And why does any of this matter? Our innate human curiosity has fueled our journey of scientific understanding and is why you're all here today. We seek to answer the larger questions of who we are, how we got here, and if we are unique, or rather, what is our place in this universe? The significance of these questions is profound, and it links us to the greater cosmos. As Dr. Filipenko talked about yesterday, in 1998, there were published observations of type 1 supernova that suggested the expansion of the universe is accelerating. Dr. Lawrence Krauss was one of the first physicists to suggest that space is composed of dark energy, making up approximately 70% of our universe by volume. Although we cannot see dark matter or dark energy directly, many of the scientists that are here today and others around the world are looking at its effects on the visible universe. Krauss has gone further by examining our current understanding of the universe in order to ascertain how we got here. By a universe full of stuff such as our own, how could it result from nothing by natural processes? So although we have many spirited young speakers with us today, and even younger Lawrence Krauss received his Bachelor in Physics and Mathematics from Carleton University in Ottawa, and his PhD in Physics from the Massachusetts Institute of Technology. He is currently a Foundation Professor and Director of Origins Initiative at Arizona State University. He has published more than 200 scientific articles, many about the physics and astrophysics that we're discussing here. Krauss has also authored several celebrated books, which you can get in the bookmark across the way, hint, hint, including some really great books on the fear of physics, about Star Trek, about the atom, and a universe from nothing. Further, he's the recipient of numerous awards, including the American Association for the Advancement of Sciences Award for Public Understanding of Science and Technology, and the Julius Edgar Lilienfeld Prize of American Physical Society. He was even nominated for a Grammy Award for his liner notes for the Telarc CD of music from Star Trek. This guy has literally done everything. He has even received the Colbert Bump for his book, A Universe from Nothing. In his abundant spare time, he has been working on and created a documentary film called The Unbelievers with fellow renowned skeptic, atheist, and evolutionary biologist Richard Dawkins, which is currently being released in limited cities and I hope to eventually see. The film follows Krauss and Dawkins as they speak publicly around the globe about the importance of science and reason in the modern world. As a science educator and advocate, Krauss is also an active and respected member of the skeptics community. I bring this up because I first heard Lawrence speak at the Amazing Meeting in Las Vegas in 2011. After watching him stand up to a very spirited discussion with Neil deGrasse Tyson on the future of manned space missions, I was a little intimidated, but more so excited and challenged by the controversial ideas Krauss presented. As you may have noticed already during this conference, he is not afraid to voice his opinion, confront disagreement, or initiate thought-provoking discussion. From his exceptional taste in shoes, which you'll get to see in a moment, to being quoted via tweet by Miley Cyrus, or to his impressive IMDb webpage, I cannot think of a more interesting, passionate, or accomplished scientist to engage us all on the universe and its limits. To quote Lawrence Krauss himself, so don't get mad at me, "The amazing thing is that every atom in your body came from a star that exploded, and that the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You can't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution, weren't created at the beginning of the time. They were created in the nuclear furnaces of stars, and the only way they could get into your body is if those stars were kind enough to explode. So forget Jesus, the stars died so that you could be here today." Whether that quote inspired you and left that awe-induced tingling feeling that I get in my body, or it rocked the boat for you a bit, I cannot wait to see what Lawrence shakes up today and the important discussions that will ensue. It is my great pleasure to introduce to you the sixth speaker of the 49th Annual Nobel Conference and his talk about a universe from nothing, as he challenges what you may think you know about the universe and its origins and ignite your imagination of what lies ahead. Please help me in welcoming a rock star of my scientific world, a man who is obsessed with nothing, Professor Lawrence Krauss.
Thank you. That worked. Thank you. Thank you, Danielle. Thank you, everyone here, Chuck and everyone else, for organizing this. It's been remarkable. First thing I'm going to do is get off the podium because I don't like podiums. I want to thank Chuck well, first of all, actually, as many of you can know, I like to try and one-up my colleague Frank Wilczek whenever I can, and I want to point out that this is better than his because I won't actually take off my shirt during the talk, So thanks to that. To Chuck, I want to thank him for allowing me to speak sixth after 2 talks on cosmology. So the talk with the universe from nothing, I kind of thought there'd be nothing left to talk about, and I figured that's what he would want me to do. But I'm going to try. I'm going to try anyway. And I think actually I've thought about there'll be some overlap, but Alex's talk and George's talk allowed me to build, I think, on some things that they've said and put them together in a way that I hope will enhance things. And really what I want to do, and this is really what I think all of the speakers has tried to do. It's one of my favorite quotes, and I began at least one of my books with it. I'm also, by the way, not going to use that stupid arrow because I've learned that actually I checked empirically that you can actually see the screens from the back of the room. So if I do this and this, you can actually see what I'm doing. So it's easier for me to do that. But really, the most exciting part of any mystery is getting to the starting point. And hopefully what we've all done, and what we'll do today and yesterday, is get you to the starting point, because they're wonderful mysteries. And there are young people here who are going to carry on science the next generation. It's those mysteries that should inspire you. The science, we too often teach science as if it was, especially physics, as if it was done 200 years ago by dead white men. And it's not. They're full of mysteries. And I hope that you will be inspired to solve the problems that we've been talking about here today. In any case, okay, so let's begin. The question that Danielle mentioned is an interesting question. And why is there something rather than nothing? It's really inspired humanity since humanity's been thinking about that. How did we get a universe? How did everything we see get here? And it's been the source of constant speculation from religion to philosophy and science. And what's amazing is that science is beginning to at least be able to confront a version of that question. And that does upset some people, as we'll undoubtedly talk about. But what I want to show you is the amazing results that couldn't have been talked about at a Nobel Symposium. We just superimpose this image on top of this one, placing that galaxy on top of itself. What do you see? Exactly what Hubble saw. And the point is, it doesn't matter what galaxy you pick. There's the image that Hubble saw. Let's take another galaxy, put it on top of itself. Everywhere you are, everything is moving away from you. And that's exactly what Hubble saw. So what Hubble told us is there is no center of the universe, or every place is a center. It depends on how you like to think about things. But really what's important is that the universe is expanding. And the fact that the universe is expanding changed everything. Again, it's so permeated the public consciousness that the universe began, well, except in certain states like Arkansas and Ohio and a few others, that it began 13.8 billion years ago. But the fact that the universe began in a Big Bang is so much a part of popular culture that we forget that less than a human lifetime ago, that was not the conventional wisdom in science. The conventional wisdom in science, and when Einstein was developing general relativity, was that the universe was static and eternal. It had been around forever, and it would be around forever. It seemed reasonable when you looked out at the sky. And so the universe having a beginning changed everything in science, and also obviously in philosophy and religion. And it changed everything in science also because if the universe was dynamical, the natural next question was, if the universe had a beginning, how will it end? And Alex talked a little bit about that, and I'll talk more about it. Because if the universe is expanding, the natural question then becomes, will that expansion stop and recollapse in the Big Crunch or something else? And the answer to that question depends. It turns out remarkably, the only way to actually consistently describe an expanding universe is to use the laws of general relativity. Because general relativity is the first theory to describe not just how things move in the universe, in space and time, but how space and time themselves dynamically respond. And what Einstein told us is that space and time dynamically respond to the presence of matter and energy by curving and potentially expanding. And so what Einstein told us is that the future of the universe depends upon how space responds to the presence of matter and how much matter there is. And we present pictures of that, and I'll show a picture. It's always hard to do, because it turns out our universe, because space responds to matter, space can curve in the presence of matter. And that means it turns out, and Frank gave a beautiful talk on geometry, that our universe can exist in one of 3 different geometries, so-called open, closed, or flat. Now, it's hard to picture these. As Frank was pointing out, it's hard to picture a 4-dimensional universe in general. It's hard to picture a curved 3-dimensional universe because we live in in a three-dimensional universe. So we draw pictures, two-dimensional pictures to guide the eye, but that's all they are. So here, it turns out in 2 dimensions it's the same thing. You can have a closed universe, which is a surface of a sphere in 2 dimensions, a flat universe like a piece of paper that's flat, or an open universe like a saddle. But these just guide the eye. In a real closed universe, we're talking about the curvature of 3-dimensional space. And you can't picture that easily. You can write it down mathematically. We can talk about what it would seem like. For example, in such a universe, if you looked far enough in that direction, you'd see the back of your head. Okay? So we could talk about that, and it all sounds very nice, but what's really interesting, and the reason physicists cared about that, in fact, the reason I got into cosmology, because I got into cosmology because I wanted to be the first one to know how the universe would end. It seemed like a good idea at the time. And 30 years ago, it's been a revolution in our understanding of the universe. It's allowed us the temerity to begin to address these questions, not answer them, but address them, and I think that's what makes it so exciting. Okay, so there are 2 ways to answer that question. One way is to write a book that begins like this. It doesn't tell you anything about anything. And now Frank may think I'm being provocative, but of course I'm really happy to see that my good friend George Coyne agrees with me about this. And I really always hesitate to say that George Coyne is a good friend of mine because I'm always worried he'll be excommunicated. But he is. But really, if we want to learn about the universe, the way is not to think about a book written before we even knew the Earth orbited the sun, but to ask the universe. And you've seen this image a lot in different forms, the Hubble Deep Field. But the way, if we want to learn about how the universe might have come into being, and ask those questions because it did come into being. And it's a physical universe, and if we want to address these questions physically, we have to look at the universe and ask the questions. And that's what I want to talk about. And the universe has changed our picture of everything more in the last 30 years than perhaps the last 2,000. And it's an incredibly exciting time. So Alex talked a lot about Hubble and the expanding universe. I won't. There are 2 things I want to add to what he did. One is he didn't mention Hubble's most important characteristic, as far as I can tell, for the young people here especially. Because Hubble gives me hope for humanity. Because he began life as a lawyer and then became an astronomer. And so for all of you who are thinking of law school, there's hope for you after that. That's the first thing. The second thing is, especially with the questions after George's talk, and George happily once again showing us we're at the center of the universe, I thought I might also complement what Alex said a little bit to give you a different way of understanding that we're not. And this is useful, I think, because I often tell students that in physics, the first time you see something, you don't understand it. And the second time you say, I've seen that before. And so there's a lot of familiarity that helps with that regard. So anyway, Alex was kind enough to give me the version of the slide he showed before. This is what Hubble discovered, which is that everything's moving away from us, and we codify it in some relationship that the velocity of objects is proportional to their distance. And that makes it look like we're the center of the universe. And he gave one example, but I'd like to give a different one, which I think, for me at least, helps me understand that this doesn't tell us we're the center of the universe. It tells us that the universe is uniformly expanding. Now, the real problem is myopia. We are actually stuck in our universe. Well, most of us are. The Republican Party clearly isn't today, but you can. But anyway. So the way to see this is to get outside of our universe. And I can draw a universe we're outside of. Here's a universe that has galaxies at regular intervals. And just so you don't feel bad over here, I'll point these. And you can see if you're standing outside of that universe that it's a little bit later. It's expanded. The distance between all the galaxies is bigger. And the question is, what would you see if you lived in that universe? It's quite simple. Just pick a galaxy, any galaxy, say that one. And to see what you'd see,